Morning. What we have seen so far is an algorithm to do model checking of LTL. And we have seen an algorithm that checks whether a finite transition system satisfies an LTL formula. And the way we did this was by taking the negation of this formula and then converting it into an automaton. And we have seen that this procedure actually has a complexity which is something in the form linear in the size of the transition system, but exponential in the size of the formula. The question today is, can we avoid this exponential blow-up? The answer will be no. And the way to answer this is that we're going to deal with the theoretical complexity analysis of the LTL model checking problem. So today the topic is about complexity of LTL model checking. So what we have seen so far are the main steps of the LTL model checking procedure. As I said already, we take the negation of the LTL formula and construct a Buchje automaton for this. And then what we do is we do persistency checking in the product. We're checking whether you can only finitely often get to an accepting state. This construction is exponential in the size of the formula, and remember the main reason for this is that we took all the subformulas, but in particular we took subsets of those subformulas as states, and there are 2 to the power, the length of the formula, many subsets, and that's the reason of this exponential blow-up. So this persistency checking can be done in linear time on the size of this transition system, and this is linear in the size of the transition system and the automaton. So the total complexity is, as I already wrote down, the size of the transition system, and it's exponential in the size of the formula. Good. Today we're going to show and prove that the LTL model checking problem is p-space complete. Okay, actually I'm going to show you 2 things. So this is the problem that we have at stake, and first, it's not just for fun. I think there's more important information behind this, and I will get to this later when we discuss CTL. I'm going to show you its co-NP hard, and then we get to the p-space completeness. So let's do a brief reminder of complexity classes. I guess you're familiar with this from the lectures on complexity and analysis book, computability and complexity. So here we're talking about the problems that are decidable, and those decidable problems can be categorized in several complexity classes. So one of the famous one is P, which are known to be the, in quotes, easy ones. These are the class of decision problems that you can solve in polynomial time in a deterministic way. Deterministic means there is no guessing. Then there is a larger class, it's NP, which is the class of decision problems that you can solve still in polynomial time, but now you need something like non-determinism, so every now and then guess something. So, and then we all know that there is the class of NP complete problems. And what are NP complete problems? Those are problems that are in NP, but in particular, all NP problems can be polynomial reduced to those NP hard problems. So this NP complete. So if you satisfy 1 and 2. Now today what is important, so this is how you can look at it. These are the NP complete problems. These are the NP hard problems. They can all be mapped onto those NP complete problems. Then there is the set which is important for today. It's the co-NP. Co stands for complement. So this is what you might expect. This contains the set of decision the complement of the set of decision problems which are in NP. So you take a problem in NP, you take its complement, you typically get a problem by definition in co-NP. Similarly, you have a set of co-NP complete problems, right? So that's very similar to NP complete problems. So these are problems that are in co-NP, and they are co-NP hard, which means any co-NP problem can be polynomial reduced to those problems. So you pick any problem here, which is also in, I think, the next slide, in co-NP. You can always map that to this co-NP complete problem in polynomial time. And then it's not hard to see that L is co-NP hard. So a decision problem is co-NP hard, which means it lies somewhere here. If and only if its complement lies on the other side, which means the complement is NP hard. Yeah? And this is sometimes useful because if you want to prove that a certain problem is NP-hard, sometimes it's easier to look at the complement and prove that it's co-NP-hard. Good, so there is this problem L, and then its complement is over there. Good. Today what we're going to use, and therefore we need this, is that we're going to consider the LTL model checking problem, and we're going to show that this is co-NP-hard, and then it follows that the complement of this thing is NP-hard. Okay, that's saying the same thing. So I'm going to concentrate on the left thing. The LTL model checking problem is co-NP-hard. Later we're going to see a more precise analysis, namely p-space completeness. But the analysis as such is, I think, quite interesting. So this is the claim. The LTL model checking problem is co-NP-hard. So how are we going to show this? We're going to provide you a polynomial reduction, and that looks as follows. So I look at the Hamilton path problem in graphs. The Hamilton path problem in a directed graph means, does there exist a path that visits exactly every node once? Yeah, that's the Hamilton path problem. This is known to be NP complete. Yeah. And what we're going to show is we're going to take the complement of the LTL model checking problem, and I'm going to provide you a polynomial reduction to the Hamilton path problem. So what's the complement of the LTL model checking problem? Well, you have a finite transition system and an LTL formula phi. And now the question is not does T satisfy phi, but it's the complement, does T refute phi? So does T violate phi? Good, this is NP complete, and by showing this we prove that actually this problem is NP hard. And therefore the LTL model checking problem is co-NP hard. Yeah? Remember, this is the complement of what we want to show, and remember this mirroring with NP and co-NP. Good. So how does this work? Let's first look at the Hamilton path problem. So what's the Hamilton path problem? You have a finite directed graph, not necessarily acyclic, it can have cycles. And does G have a Hamilton path? That is, does there exist a path that visits every node exactly once? So you're not allowed to visit a node twice. This is bad. Good, so let's suppose that this is my finite directed graph. Question, is there a Hamilton path in this graph? That means, is there a path that visits every node exactly once? Well, you could, for instance, start here, then we go there, then we could, for instance, move here, right? Then we can move there, and then we do there. Yeah? So it's a kind of a zigzag through the graph, and you have a path that exactly visits every node once. So indeed, this has a Hamilton path. This graph has no Hamilton path. Why not? Well, suppose you start here. I mean, because we have to visit this node anyway, right? So why not start there? So you move to the left. Yeah, and now you see already, in order to visit either this one or that one, you can move to the right, but then the only way is to go back to the center point in the middle. So you cannot visit all the vertices in this graph by visiting every vertex exactly once. Yeah. So this graph has no Hamilton path. Good, this is an NP-complete problem, so this is intrinsically a hard problem, provided P differs from NP. So let's look at the polynomial reduction. So remember, we take the Hamilton path problem, and we're looking at the reduction from the complement of the LTL model checking problem. Does your transition system refute the formula? That's the problem we are considering. So the way we're going to do this is we take the problem description on the left-hand side, and we're going to map this, and this mapping needs to be possibly done in polynomial time to a problem instance on the right-hand side. So the instance on the left-hand side is a finite directed graph. On the right-hand side, we're going to build a transition system as well as an LTL formula. And then the correctness criterion will be G has a Hamilton path if and only if, yeah, this problem means is a solution, which means the transition system refutes the formula. Yeah? Remember, we look at the negation. This becomes also important when we are going to construct phi. Good. So I do this by means of an example. I think the formal definition is then pretty easy to understand. Let's suppose this is my finite directed graph. So now we're going to construct a transition system from this. And the way to do that is we just copy the graph. The only point is that we can start at any point. And why is this? Well, intuitively speaking, I can start my Hamilton path in any vertex of the graph. So in my transition system, I make all those states initial. Good. What else do we want? Well, at some point, if we finish the Hamilton part, we actually, in the transition system, have to, well, we are going to model this by a special state in the transition system. I call this the trap state, which is T. And what I do is I make a connection between all vertices in the transition system, in the graph, to T. Intuition, here you have a Hamilton path. At some point you have visited exactly all vertices, and exactly by visiting everything once, then you stop, right? How are we going to model that we stop? This is by being able to move to the T state. Where can the Hamilton path stop? It can stop in any vertex, so we have a transition from any state to this trap state. Once we stop, we stop. So that means that we only have a self-cycle, there is no way to go back. So this is the intuition. We transform this graph into this transition system. And now we have to check the formula. Yeah? So what is the idea? The idea is that this graph has a Hamilton path if and only if this transition system, which means this transition system, does not satisfy the formula phi. Yeah? So phi needs to characterize the negation of the existence of a Hamilton path. Okay? Let's ignore the negation for the moment. What do we need to say here? Well, first of all, we need to be able to say something that we are going to visit states. How are we going to do this? We're going to say that the set of atomic propositions is V. And that means I'm able to say the atomic proposition, I'm currently in V2. In the next state, I will be in V3, and so forth. Once I have visited V2, I will never visit V2 again. Now, these are the kind of properties that we need in order to express the existence or complement the non-existence of a Hamiltonian path. Okay, so how does this formula look like? This looks as follows. First of all, we have to visit all vertices. That's the conjunction. Okay, so eventually we have to visit all vertices. That's the first part. Ignore the thing after the conjunction. Good. Then the second thing that we need to express is that once you have visited a vertex, you should never visit this vertex again. Yeah, because you're only allowed to be there exactly once. So it's always the case that once you have visited the vertex V, from the next state on, you will never visit V again. Yeah, notice this next is important. If I would omit the next, this would be a contradiction. I cannot say V implies always not V, because that means that also this can be able to hold at the current state. Yeah? So this next is important. Currently I am in V, and then from now on I will never be in V again. From now on I will never be in V again, and this must hold in every V. Okay? A side remark which is going to be important later when we are going to discuss a couple of lectures later LTL, or CTL, sorry. This formula is, the size of this formula is linear in the size of the graph. Yeah? There is no explosion here. Good. Now, remember, we don't have to express the existence of a Hamiltonian path, but the non-existence. Remember, because we are considering the complement of the LTL model checking problem. That means this has a Hamiltonian path if and only if the transition system refutes the formula phi. Yeah? So therefore we put a negation in front. Yeah? So this negation comes from the fact that we take. Now, I hope you understand this construction. As I said, I'm going to omit the technical details. You can now transform any directed graph into a transition system and get to this formula. And this means that the LTL model checking is co-NP hard. That's the conclusion. Yeah, against back. We have proven this. This is NP complete. Now, by this polynomial reduction, we have proven that this is NP hard. This is the complement of the LTL model checking problem. So the LTL model checking problem is co-NP hard. Okay? Good. Okay. Now we're going to prove that the whole thing, model checking problem, is p-space complete. I will quickly go through the slides to show that it is in p-space, and then we're going to show the p-space hardness, which is the hardest part. Yeah? And I'm going to do that on the blackboard. So some words about the complexity class P-space. So P-space is the class of decision problems, like NP, like P, etc. But now this has a deterministic polynomial space-bound algorithm. What does that mean? This means intuitively that this problem can be solved by a deterministic Turing machine, no guessing. That's what this means. Polynomial space-bounded means that the size of the tape that you need in order to solve the problem, this is in worst case polynomial in the size of the input. Okay, so you feed this Turing machine with some input of length n. Now this Turing machine can maximally use a number of tape cells which is p of n, where p is a polynomial in n squared plus 37n plus 2 or something like this. Yeah? Good. Now what do we know about P-space? NP is included in P-space, and that means that you can do something like a DFS-based analysis of the computation tree of an NP algorithm. And the space requirements here are the recursion depth, which is the height of the computation tree. What is important is that P-space is equal to its complement. So what we have seen before was this NP and co-NP. They're not necessarily the same, right? They have some intersection. There are certain decision problems which are in co-NP and in NP. And typically this is a kind of characterization that we believe that those problems are simple. They don't have to be in P, but they tend to be simple. But for P-space, we know that this is actually the same as the complement. And in particular, we also know, and that's interesting, there's a Savage theorem that says, okay, whether you have a deterministic space-bound algorithms or a non-deterministic one, by non-determinism you don't gain anything. Yeah? So these two complexity classes coincide, which was different, at least as far as we believe so far as computer scientists, than P and NP. Yeah? P is included in NP. And here these are really the same. Famous algorithm by a famous theorem. Good. So in order to prove that a problem is in P-space, it suffices to provide a non-deterministic polynomial space-bound algorithm. Yeah? You want to prove that the problem is there, but because of this equality, it also suffices to prove the problem is there. What does this help you? Well, you can use the fact that you now may guess. Yeah? That's the whole issue. And this is sometimes very useful. Good. So this is the picture. So again, P-space are the class of decision problems decidable in deterministic polynomial space. P is included there. Here is co-NP and NP, the things that we just have seen before. Here are the co-NP complete problems and the NP complete problems. Here was the LTL model checking problem that was in co-NP hard, right? And this was NP hard. Yeah, so that lies over there. And what we're going to show is that LTL model checking is actually P-space complete. So it is as hard as any problem in this P-space complexity class. Good. So what does it mean to be P-space complete? Very similar to NP complete and co-NP complete. Two constraints. It needs to be in the class that you're considering, so it needs to be P-space, and it needs to be P-space hard, which means that there needs to be a polynomial reduction, right, for all problems in P-space from K to this P-space hard problem. Good. As P-space is co-P-space, remember the complement of this whole thing. So if you would take this picture and you would take co-P-space, this is exactly the same blue box. Yeah? So it's different from the green and this inner NP box. It's the same. And that means that we can also show the following. L is P-space hard if and only if the complement of L is P-space hard. Yeah? Because we know that if L is P-space hard, its complement is co-P-space hard, but because co-P-space is the same as P-space, this amounts to be proving the same thing. Yeah? This is different from what we just have seen. We have proven something to be co-NP hard by showing that its complement was NP hard. Yeah, there the difference made, I mean there really is a difference in the complement, here it's not the case. Good. Then we also know that this set was the same as NP. Right? Remember my remark, this was the Savage theorem. Being able to guess doesn't matter, which means that if you want to show that the problem is in P-space, it's equivalent to proving that this complement is in NP space. Yeah. Complement because the complement is the same, and P space because P space is the same as NP space. Yeah. So all these classes collapse together. So you can play with this if you want to prove something. Yeah. Sometimes it's easier to prove that the problem is here rather than proving that it's there. Or sometimes it's easier to prove that the problem is there rather than proving that it's there. Yeah? And you can use this fact because those classes here coincide. Good. So why is this important for LTL model checking? Well, the LTL model checking problem, as we all know, means that you take all the parts in the LTL, in the transition system, they need to satisfy the LTL formula. The complement is, does there exist some part refuting the formula? Yeah? We want to show that the transition system violates the formula, which means there needs to be a counterexample. This is my counterexample, and that means that counterexample violates the property we want to check. Good. So I hope it's also clear that the existential LTL model checking problem is now going to be similar to this complement. What we're going to do is we're going to take T and we're going to take the negation of phi. So T, and we're going to take the negation. And that means that we are interested in, does pi, this counterexample, satisfy the negation of what we're interested in, which is the same as saying it refutes phi, right, for some part. Good. So what we can show is that the existential LTL model checking problem is in NP space. NP space is the same as P space, it's the same as the complement. All these things are the same. And we show, and that's the hardest part, the existential LTL model checking problem is P space hard. Good. Let me first sketch, and I really want to not spend too much time on this. The details are in the slide that this problem is in NP space. Yeah? So we want to show it's P space complete, so we have to prove it's in P space. P space is the same as NP space, so if we have proven the first thing, we are done with the first constraint. Then we want to show it's co-NP, it's P space complete, which means we have to show it's P space hard. Second part. So here you see that I use the fact that those classes collapse. P space is the same as NP space. Why is this relevant? Now I can use the fact that I can guess. Why is this relevant? I can use the Boogie automaton construction, as we're going to see. Good. So from this it follows immediately that the LTL model checking problem is in P space. Yeah? Why is this? NP space is the same as P space. This is the complement of this thing. Yeah? And co-P space was the same as P space. Good. If we have proven this, then it means that this problem is P space hard, but because P space is the same as co-P space, it means the complement of this problem is also P space hard. And that's the LTL model checking problem. Yeah? So I'm using in two different ways the fact that P space is the same as NP space, it's the same as co-P space. Good. Okay. The existential LTL model checking problem, a finite transition system and LTL formula, does there exist a part that satisfies the formula? Satisfies, remember, because what I do is here I just take the negation, right, which is the same as negating phi. Yeah? So this is absolutely the same as we have done before. Goal, what do we want? We have to find a criterion that tells us, well, such a counterexample does exist. So we need to have a criterion that says, okay, there is a part pi, and that criterion needs to be able to be checked in what? Well, non-deterministically. Why non-deterministically? Well, I want to show it's in NP space, so I can use the non-determinism. What else can I use? Well, I need to show it's in P space, so this criterion needs to be able to be checkable in polynomial space. If I need more space, I'm outside my complexity class that I'm considering. Good. So the idea is we're going to use this GNBA that we have already constructed in the algorithm. So I'm using exactly the same automaton as we used in the algorithm. Good. So this is at stake. A finite transition system and LTL formula, and this problem, is there a path satisfying phi? which is different from the LTL model checking problem, because there we were saying does for all parts satisfy phi. So the existential quantification, there is a part, is important here. So we're going to check whether there is a part satisfying phi, and we're going to do that by means of a non-deterministic polyspace algorithm. So let me sketch this non-deterministic polyspace algorithm. And the way we do that is by means of using this GNBA. Good. So what are we going to do? We have this automaton. We have to find a counterexample. I have no clue where this counterexample can be. So what I'm going to do is I'm going to exploit the non-determinism. I'm going to guess. So I'm going to guess, well, maybe this is a part that leads me to a counterexample. Maybe that one. Yeah? So I'm going to guess, which is using the non-determinism, a periodic part. What does that mean? Well, this part is, has a finite prefix and at some point ends in a cycle. Yeah? And then we traverse this cycle infinitely often. Where are we going to do this? We're going to take such a part in the product of the transition system with the Buggy automaton. Yeah? Good. And then we need to check that this part satisfies the property, right? Because we were interested in checking, finding a part satisfying the property. So we also need to check whether the part that we just have guessed satisfies this condition. Good. I'm going to skip the details about the GNBA. So what's the criterion? There exists a part satisfying phi if and only if there exists some initial part fragment in the transition system. Yeah. So there exists an initial part fragment starting in some initial state, then we reach Sn, and then at some point we reach Sn plus m, such that this is in the transition system, right? Now we're going to look what does that mean in the automaton, because we take the synchronous product. Yeah. So in the automaton it means that this fragment in the transition system needs to be matched by a run in the Buggy automaton. For what? Well, you just take this as an input word. Remember, we always look at the atomic propositions that are valid in those states, so we take the trace of this thing as an input word to the automaton. Such that, what do we want to have? We want to have that we have a cycle. Why do we want to have a cycle? Well, we only have finitely many states. We want to have an infinite run, so we need to find some cycle. So that means that in the product, we have to be able to show that if we are in state Sn in the transition system and in state Bn plus 1 in the Buggy automaton, this is the same as being in the last state here and the last state there. Why is this shifted plus 1? Remember the product construction, which was always shifted by one position. Yeah, that's the plus 1 here. Good. What else? We need to check that this cycle satisfies the acceptance condition. What does that mean? It means that if there is an until formula in one of the states on the cycle, in the Buggy automaton, then you also need to be able to fulfill this until formula on that cycle. What does that mean? It needs to be that there is some state in the cycle that also has psi2 there. Otherwise, the until formula is not satisfied in the part. Good. For the rest, this n has a certain length. We are not allowed to guess arbitrary length. Why not? Yeah, because we have this space construction. Yeah, so it needs to be polynomial in the size of the input. The input is the size of the transition system times the number of states in my automaton. Remember, the number of states in the automaton is exponential in the size of the formula. Good. And for the rest, the size of the cycle. Yeah, why is this? Well, this is the same. The size of the transition system times the size of the automaton times the cardinality, the size of the formula. Why is this? Well, phi can have several until subformulas. Remember the GNBA construction. For every subformula you have an accept set. You have to fulfill all of them. Yeah? And fulfilling all of them leads to this multiplicative factor phi. Good. So what's the NP space algorithm? It's solvable in the following way. We guess non-deterministically a part in this product. So we take the product of the transition system and the Buggy automaton. The Buggy automaton has been constructed in the same way as we had done for the algorithm, for the LTL model checking algorithm, and now we guess a part, non-deterministically. This guess may be wrong, may be good, and we just guess, right? And then what we do is we check whether the guess part meets the acceptance condition. What does that mean? We are going to guess two numbers. So first we guess a part. Now we need to guess, well, we need to have a finite prefix, and then we have this cycle. Where do we start the cycle? Yeah, so we're going to guess this. So we're going to guess two natural numbers, n and m, such that, well, satisfying the criteria before. So that means that this k is exactly the number that I just explained, the number of states in the transition system times the number of states in the automaton times the size of the formula, because we have to fulfill all the until subformulas. Good, so we guess a part in the transition system. Yeah. Then we guess n plus m plus 2 subsets of my closure. And then we check whether the following conditions hold. So I guess a lot. Yeah, I guess a part, I guess the n, I guess the m. Yeah, so I guess the length of the prefix, I guess the size of the cycle. And now what I need to check, yeah, is my guess correct or not? So now I have to check a couple of conditions. I have to check whether indeed it's a cycle. So if I am here in the transition system and there in the automaton, this is the same state in the product as the one at the end of the cycle. I need to check that this is an initial run. An initial run of what? Well, of the trace of the part that I just have guessed in the transition system. And I need to check that all my until formulas are fulfilled. Yeah. And this you can do all in polynomial time. So this you can, the checking is not the hard part. What is important is the way that you see how I guess. Yeah? So I really exploit the fact that p space is the same as np space, and this n helps me to get the proof. Good. Okay. So what is the conclusion of all these details about guessing and so forth? We now know that the existential LTL model checking problem belongs to np space, and that's the same as p space, so it belongs to p space. Are we done? No, we want to show it's p space complete. So what is left is the p space hardness. Yeah, so this is fine. It remains to prove the p space hardness. Good. So what we're going to show is that for all problems in p space, that they are polynomial reducible to the LTL model checking problem. How are we typically going to prove this? We're going to pick a problem with this p space hard and polynomial reduce it to the problem that we are considering, the existential LTL model checking problem. So what are we going to do? I'm going to take a deterministic Turing machine. Yeah. Why deterministic? Well, I'm going to use the fact now that we are p space. P space means deterministic computation polynomial space. So now in the hardness proof, I want to get rid of this guessing, yeah, because it only complicates matters here. So I'm going to use the fact that this Turing machine is deterministic. What is the Turing machine going to do? Well, it's going to decide the decision problem k for us. Then we need to have this polynomial space. So what am I going to do? I'm going to get to say that there is a polynomial p, such that the Turing machine starts with an input w, and the number of tape cells it needs in order to decide whether it needs to accept w or reject w is polynomial in the size of the input. Yeah? So it visits the polynomial number of tape cells in the size of the input. Good. So what I'm going to show is the following. We're going to provide the following reduction now. This decision problem, yeah, is represented by a deterministic Turing machine deciding k. Good. Then what I have is I have this deterministic Turing machine, and now I'm going to give a polynomial reduction to an existential LTL model checking problem. That provides us, because this is p space hard, it follows that this will be p space hard. Yeah. Now the reduction. The reduction is the following. I take a deterministic Turing machine and an input word, a finite input word, w. We're going to provide a polynomial time reduction that going to construct a transition system. This is going to depend on the Turing machine. It's going to depend maybe on certain aspects of the input word, plus an LTL formula phi, such that the following holds. The Turing machine accepts w. which means W belongs to K, which means we are able to decide K, if and only if there is a path in my transition system that satisfies phi. There is a path. Remember, I'm considering the existential model checking problem. Yeah? So always talk about the existential part. Good. So the main job that we have to do is, how on earth does this transition system look like depending on the Turing machine, and how does this formula phi look like? Good. Don't worry that I'm going to ask this in an exam, but this is a key result in LTL model checking. By the way, it's due to the following people that you all know. It's Sisla, Prasad Sisla, nowadays a professor in Chicago University of Illinois there, and Clark. And this is a result from 1985. Clark is Edmund Clark Turing Award winner in 2007. Good. So let me first, I think the easiest way is to just draw. I will just draw the Turing machine and then explain how it works. Good. So what we want is exactly this polynomial reduction. Input word W, deterministic Turing machine M, mapping it to a transition system and an LTL formula phi. Good. I'm making the drawing, and then we're going to see that the transition system is as follows. This stands for 0. It's not something like an accepting state. And here we have 1, we have 2. What is P? P was this polynomial. Yeah, remember, I can use polynomial many tape cells, and this is my polynomial P, and this is also a state. And here I end something of the form Pn, and this is also a state. Good. Then there are all states in between. So here there are many states in between. Here are many states in between. Here are many states in between. So in between any pair of those states there is such a sequence, such a set of other states, and there are transitions to all of them. So this can move here, it can move there, it can move there, this can move here, this can move here, this can move there, this goes there, this goes there, this goes there, this goes here, this goes here, that goes here, that goes there, etc. Yeah. Good. Okay? And then there is a possibility to go back. Good. Good. The first observation we make, the size of this transition system is polynomial in the size of the original problem. Yeah? That's good because we want to have a polynomial reduction. Good. What are the states? So the idea is the following. These states in the middle. So this is, for instance, the state that is a state which is a triple. It's QA1. I'm going to explain this in a minute what that means. This is, for instance, QA2. And this is QA3. And this is, for instance, something of the form, what is it, QA and then Pn minus 1. Good. Let me explain those triples. So what does that mean? So we have the set of states. So now I'm going to formally write this down. What we have is the set of states was 0, 1 up to Pn. These were the states that I drew initially. And then all the states in between. So those, let's say, diamond states. These have the following shape. They are of the following shape QUI, such that, or QAI, sorry, such that Q is either, and this is the Turing machine state, or it's something like a special state, it's called star. Or A is an input symbol, So these are the input alphabet of the Turing machine. And then we have a position, and this position is any number, now be careful, strictly larger than 0 and at most, why is it at most? I don't see this. 1, I made a small mistake, and that is that this n minus 1 needs to be n, sorry. So this is at most Pn. Good, what do we have? We have those numbered states, 0, 1, 2, etc. And then we have those states that follow this, let's say, diamond shape. And they are of the following shape. It's a state of the Turing machine with an input symbol and I, which is just a number. Intuitively speaking, it tells you Q. This is the state of the control state of the Turing machine. This is the input symbol that you just have read. And I means this is the ith tape cell. Yeah? So in the Turing machine, you would number the tape cells, right? So here is your tape of the Turing machine. How many tape cells do we have? Well, polynomial many. Yeah, so we number them, and that means that we have states of 1, 2, 3, etc. up to Pn. These are the tape cells. And then we have a control state, so maybe we want to model that, for instance, we are currently, the control state is Q. And the head of the Turing machine is pointing to cell I. And at this position there is symbol A. Good, so what's the idea? The idea is that a path fragment in this transition system from state 0 to state Pn represents a configuration of the Turing machine. So we have a tape content. So we model that we have a tape content which is something of the form A1, A2 up to APN. Yeah. So this is AI, this is, well, we start at A1, A2, etc. Yeah, up to APN. Then we have a state. And we need the cursor or the pointer, the head, well, better, cursor. Cursor points to cell I. Good. Yeah, and this is encoded as follows. So this is the path fragment. So how is this path fragment encoded? This is the path fragment that looks as follows. We start in 0, then we have star A1, 1. So now you see where I need the star for. The star are, you have those elements in the tape, but the cursor is not pointing there. That's what star means. So this means cursor does not point to tape cell 1. Tape cell 1. Now you go to 1. Now you have the same for tape cell 2. Let's assume I differs from 1 and 2. So this means we have star A2, 2. Now we get to 2 and this follows, right, like this, up to some position I minus 1. Now you get something of the form Q, AI, I. So this is different from star. All the other ones are all stars. Yeah? There is one position where we have Q, because the Turing machine can only point to one position at the tape. And we store at that point also the control state. Yeah? So this means basically B and C at the same time. Yeah? The control state is Q and we're pointing to A. To I, to cell I. And then we have here I, and here we have something like star AI plus 1, I plus 1, etc. up to, well, this goes on up to Pn. Yeah? This is 1 in your Turing machine on the top. This is 1 going from 0 to Pn. This encodes one configuration of the Turing machine. What happens if the Turing machine moves? Well, if the Turing machine moves, we take the back edge. The edge that goes from Pn to 0, because then we're going to encode the next configuration. Okay? So let me show this by means of an example. By the way, is this clear? Is there any question so far? It's a bit detailed, but yeah.
There might be a mistake in the second to last figure state. Maybe it should be P of n and then -1?
No, I don't think so. Because left from 1 there is 1 with a 1, left from 2 there is 1 from a 2, so left from Pn there must be Pn, is my reasoning.
No, it's a bigger state.
Yeah.
Just label it P of n-1.
Yeah.
Should actually be P of n minus 1.
The one that is labeled
On the topmost line.
polynomial.
Okay. I don't get it yet, but so this is okay, right?
Yeah.
But this is not okay?
Yes.
What should it be?
P of n.
Ah, of course, yeah. Pn brackets -1. Yeah, okay, good. Fine, fine, fine. Let's fix this. Can you cut it from the tape or? Yeah, you're absolutely right. This is not a polynomial in terms of n-1. This is indeed stupid. Yeah. This needs to be, that's what I also meant, Pn -1. Sorry, yeah. It's good that you are all awake. Very good. Absolutely. Good. Other questions? No? Good. So now let's do a computation. Well, not the whole computation. Let's do one transition of the Turing machine. Okay? So let's assume, where do I have this? That we move. Okay, so this is the current configuration that we just have seen here on the, so this is the current configuration. Yeah, and now we move. So how to model one move of the deterministic Turing machine M. And let's assume that I'm going to take the transition that delta QA is PB and then -1. Okay, what does that mean? It means if the Turing machine currently is in control state Q, and the next input symbol is A, it's going to move to the control state P. It's going to replace this A by B, and the head, the cursor, is moving one position to the left. Okay, so move from Q on A to state P, replace A by B, move cursor one position to the left. Good. So how I'm going to model this? This means the current configuration is here. So the current configuration is a path fragment that goes from 0 to Pn. Now I'm going to take this transition. This transition means that I'm going to take this transition in a transition system. Yeah, so this back edge models the move of my Turing machine. Good. And now what we are going to encode is the resulting configuration, again in terms of a path fragment. So what's the resulting configuration? So the resulting DTM configuration is modeled by the path fragment (0 star A 1 1 1 star A 2 2). So I'm assuming in the beginning nothing changes, right? And at some point I get to position I minus 1. So here I get P A I minus 1 I minus 1. I hope that I get all the I minus 1s right now. I minus 1 star B I star AI plus 1 I plus 1 PM. Good. So how to see what has happened? We go from Q to P, right? We're going to replace A by B, and we move the head one position to the left. So let's first move the head one position to the left. The head here was at position I, so the head now will be at position I minus 1. Yeah, 1 to the left. So that gives rise to this part. Yeah? We are currently in I minus 1. This says the cursor is at position I minus 1. What is the state? Well, the state has changed, right? Because the state has changed from Q to P. And I'm going to encode this here at this position, so this now becomes P. Yeah. But there is one more thing. Before moving, we have to replace A by B. Before moving. That means at position I, yeah, I think this must be an A, by the way. Yeah, if this is A, I'm going to replace this A, this A, by this B, and this is my B, which is here. Yeah? But you see, it's at position I. Yeah? So the Turing machine replaces this A by B, then moves one position to the left, and changes state from Q to P. Good. This is one step of the Turing machine. And now I hope you see that in this way you can model the whole computation of the Turing machine by means of this transition system. What is missing yet? Does somebody have a clue what is missing? Where is the input word? It's not there yet. Yeah? The only thing that I use so far is the size, namely P of n. I only use the fact that I have this polynomial space thing. I didn't use the input word yet. And this is what we're going to capture in the LTL formula. Yeah? So far we have seen how the transition system looks like, and now we have to see how the formula looks like. What does this formula have to encode? Well, it has to say something about the input word. It also has to say something about the fact that, for instance, here I was just explaining the intuition and saying, okay, if this is a configuration, there is exactly one position where there is no star. Who is going to fix this requirement? Who is going to ensure that this is always the case? My transition system doesn't. Yeah? It allows to be at this state somewhere here, where there is no star, and there at the same time. So also W needs to make sure that indeed in such a configuration there is exactly one position where there is no star. Yeah? Then I explained to the intuition that this is going from one configuration to the next configuration. Who tells me that this is the way the transition system is going to work? The transition system doesn't. So my formula has to encode the fact that I move from this configuration to that configuration. Yeah? Because my transition system is not restricting anything yet. Yeah? Good. Is this clear? So this formula needs to fix quite a bit. Yeah? It will be a huge formula, yeah, that we need in order to ensure that this is now correct. Yeah? This is only the operational modeling of the Turing machine, but now we really have to make sure that everything is indeed working like a Turing machine. We have to, for instance, also ensure that we start with a tape that only contains the input word and the rest is empty cells. This is not guaranteed yet, so this also has to be made sure by the formula. Yeah? So all this we have to encode in LTL. So what we're going to do is we're going to construct an LTL formula, and this LTL formula is phi of w. Yeah? And it also actually depends on the Turing machine M, so it's actually phi of W and M. This WM has nothing to do with the World Championship Soccer, although it looks like WM, VM, but yeah, so what is it going to be? It's going to be several parts. QW start, I write it first down and then I will explain you what it is. Phi conf, and we need to have a phi delta, and we need to have a phi x. Yeah, good. So what is this? This is the modeling the starting configuration of the DTMM on W. So this is going to model indeed that the tape starts with the input word and the rest is empty cell, yeah? Roughly speaking. Then this part of the formula is going to model that it is a sequence of configurations. What do I mean by it? A path, right? So if the transition system that we just have drawn, that was somewhere on the top of the slide, if this makes a run, every path fragment is a configuration, which means it doesn't make a mess. It doesn't get into certain paths that do not correspond to my Turing machine. That I need to make sure. Then I have to respect the transition relation, respect the DTM's transition relation. Well, actually a function because it's a DTM, yeah? Delta. It's a deterministic Turing machine. And then there is an accept. What does this mean? This is going to model the acceptance criterion. Good. So I have to explain you 4 subformulas. Good. Okay, let's start with the easy one. Phi ac. So I start from the back. This is modeled as eventually Q in F of Q. What is Q? Q is something of a disjunction over all D in sigma, 0 at most J less than Pn of QDJ. Good. So the first thing I need to explain is what am I able to express about the transition system. That means what are the atomic propositions. So I go back first to my picture. This was the picture of the transition system. So what are the atomic propositions I'm going to use here? The atomic propositions are the following. So maybe I write this down in a different color. So AP is the set S unified with begin and end. Good. So what does this mean? For every state, I can just, in the formula, address in which state we are. So in particular, I can say we are currently in 2, or we are currently in this state. Yeah? What is this state? Well, this state are those triples. Yeah? So if this is a triple, this formula is simply saying, for some symbol in the input alphabet of the Turing machine, we are currently in a state which says that the control state of the Turing machine is Q, then the input symbol is something, and it's at some position J. Yeah? So this really says, I am in Q. Yeah? This says the Turing machine is currently in Q. But of course, it needs to be expressed in terms of the transition system. So it needs to be expressed in terms of this configuration ID. Yeah? So this tells us basically the transition system is somewhere. It's representing a configuration, but it's currently in Q. Yeah? The Turing machine needs to accept. What does it mean? Eventually, we have to reach some accept state. Not infinitely often. It's a Turing machine. Yeah? It's not something like a buggy thing. It's enough to be there once. Good. Do you understand this formula? This is by far the simplest formula we're going to see. So if you don't understand this, this is going to be, yeah? Okay, good. So atomic propositions are things like, okay, this is labeled, by the way, by begin as well, as we end with 0. This is labeled with 1, this is labeled with 2, this is labeled with, for instance, Q, A, and then some sample. Yeah, and this is labeled with Pn, and now take the brackets right, -1, Pn, and so forth. Yeah? These are the atomic propositions. Good. Okay, so this is done. Now let's look at the start thing. So now I'm going to look here. I hope that's also relatively easy. Intuitively, what is the starting thing going to model? The initial part is simply that all the input are on the tape. So what is phi start W? This is next Q0 and 0i at most n next to the power 2i minus 1 ai and n good. Let me try to explain this. So this belongs to the formula above, right? Okay, what is this going to tell us? This is going to say, okay, the next thing says that we start in the initial configuration Q0. That's the initial control state of my Turing machine. So this is the initial state of the DTMM. This thing is a deterministic thing, so it means it only has one initial state. This is the initial state. Good. Then what do I need to model? I need to model that the tape is the following thing, right? The tape is position 1 up to Pn. How do we start the Turing machine? The input word is on the tape and the rest of the tape is empty. So what we have is, this is the input word, W. Let's assume the size of W is n. Yeah? So up to n, this is the first symbol of W, this is the second symbol of W, etc. Yeah? So this is W1, W2, etc. until we get Wn. What is the rest? The rest are blanks. Blanks are indicated like this. So these are blanks. Yeah? This is the initial tape of the Turing machine. Good. How do I model this? First, I have W, so this means W is on the tape. I do this from 0 up to n. Yeah, so I from 1, strictly larger. So from position 1 to n, this is going to tell you that AI is there. So actually I should not have written there W. I should have written there A1, A2, AN. Yeah? This is AI. Why do I need this 2i minus 1? Why do I not just write the first n positions? Well, this is next 2i minus 1, so this means next, 2i minus 1 times. Yeah? Why do I need this factor 2 here? Well, this has to do with the shape of this Turing machine, of the shape of the transition system. Yeah? This is one, then I have to basically skip the intermediate states, yeah? So I only have to look at those states, yeah? So every time I have 2 further, 2 further, 2, 2. Yeah? Look at my configuration. Here is the configuration. Is it still there? Yeah, there is one there. I mean, here is symbol AI. Then I have one symbol that I need to skip, and then I have A2. Then I have one symbol to skip, then I have A3, and so forth. Yeah? So this is 2 times 1 minus 1. This is 2 times 2 minus 1, etc. Yeah? Good. So that's why I have this 2i minus 1. And then the rest of the tape is blank. So this stands for blank. This means the space or empty space. The empty, blank. So this is going to say that this whole part is blank. So this goes from position n plus 1 until, including position Pn, I have blank symbols. Good. Any questions so far? No? Good. So we have done the first and the last, and what we have to do is the 2 middle ones. Conf and delta. Let's first do conf. What is conf? What does it need to express? Well, it needs to express our intuition, namely that a path fragment is indeed a configuration. What does it mean? There can only be exactly one star in this whole sequence. There's one position where it's P, all the other ones have stars. This we need now to fix in terms of the formula. Good. I hope all the brackets, no, I think this bracket is still missing, right? Good. What do we need to encode? We need to encode that this path fragment starting in the completely left state. That means starting here is a configuration. Starting here means this needs to be true. Yeah? This means we start. So start, intuitively speaking, start the configuration. This is not only the case initially, but every time we are in the begin state it needs to be true. That's where we have box. Every time we go back to the initial state, we want to encode an entire configuration. That's what this box tells us. Good. Then what is this phi q? Let me first explain this. Is the following thing. Q belongs to Q with some input symbol sigma and some I at most Pn of Q, A, I. What is the crucial part in this formula? This thing. It's in Q. So in particularly, Q differs from star. Yeah? So what this tells us is that at some position, this disjunction, at some position I, the first part of such a triple is not star. This is this part. Yeah? So this tells you, basically, sum of the positions in the configuration are of the form Q different from star, some symbol A, and some position I. Yeah? What is important is this. Yeah? So at least along this path there is at least one where there is not a star. What else do we need? We need that it is exactly one. That's what this part tells you. So if this thing holds, there is no other position at which the same thing holds. Yeah? So this says, yeah, no other position than I contains a triple of the form P different from star, some symbol B, some position J. Yeah? This is. Yeah? So for some position there is a non-star, and if such a position has this star at I, it is an I, then at all different ones, I different from J, this is not the case. Yeah? Good. The index 2 again is the same reason as before. We have to skip the states 0, 1, 2, 3, etc. Right? The only ones that we are considering are the ones that are in this branching thing. So basically the ones that are here, there, and so forth. Good. Any questions? Is this roughly clear? Yeah? Good. Now we get to the hardest part, the transition relation. I hope you still see that this length of the formula is still polynomial in the size of the Turing machine. Roughly, huh? Good. Last part. Transition relation, and I'm just giving one example because the transition relation you have to basically get a formula for every transition of the Turing machine. So this is enormously. So what I'm going to do is I give you a formula for one. And then let's see what's going to happen. And I'm going to do that for exactly the same example we have seen before, such that hopefully this is clear, intuitively at least, what we are doing there. Still on track? Good. Phi delta. Unfortunately, phi delta is a big disjunction, or a big conjunction, I should say. It's for all Q in Q, and for all input symbols, I'm going to model phi QA. So basically what you have is you have a delta QA, is something, then you have a delta Q prime B, and all these things, all these functions, right, they are deterministic, all these things are encoded by a formula. Yeah? So this is the formula phi QA, this is the formula phi Q prime B, etc. So you list all the transitions of the Turing machine. Yeah? Every transition becomes a formula. And then you take the big conjunction of all of them. Yeah? Good. I take one. Yeah, I take one such thing. So I'm going to tell you how this phi QA looks like. And then from then I hope you're able to distill how this looks. Good. I'm going to do this for an example. So the example I'm going to use is exactly the example we have done before. Namely, delta QA is PB minus 1. We move from Q to P, we replace A by B, and the cursor is moving one position to the left. Yeah? Same example as I had before, but now in terms of LTL formulas. Good. So, phi QA is box this is the start. No? So this is basically telling, okay, it's always the case that you start, always your reference, the anchor of the configuration is where you start, which is begin, which is the most leftmost thing. Right now what we need to check is, at some position we need to have QAI. Yeah? Because we have QA, we don't know at which position it is, right? It can be at any position, so therefore we have to look at all possible positions and we need to check, hey, is there this QAI somewhere? That means the transition is enabled. Yeah, so this means basically transition delta QA is enabled. No? Now we have to take the transition. This is what here comes. No? Good. Okay, so now where is defined by the following thing. Good. There are three parts. We start with part 1. So it's a conjunction of 1, 2, 3. And I start with the first thing. The first says good. Wow. What is this formula saying? This formula is saying that basically all tape cells except the one at position I are unchanged. No? Good. So I write it down. So it says all tape cells except at maybe position I. It could be that the transition doesn't change the symbol, I don't know yet, right? All tape cells except at position I remain the same. So, how do I model this? I have one configuration, the current configuration, which is this thing. The next configuration is given by, remember, going back and then the next configuration. So that means that here, if I have a C at position 2j minus 1, The other C that I want to check whether at this position in the next configuration there is also a C. So I look at the next position, 2j minus 1, but in the next thing, it's 2 times Pn plus 1. Why this factor 2? Yeah, because I have 2 Pn states. Yeah, Pn are the middle states, but remember I have always these states in between. So I have 2 times Pn states. Yeah, so this really means, yeah, let's say position J, yeah, in the next configuration. That's what it means. Yeah. It looks, I hope I have all the brackets correct, but you can check, double check. Yeah? Okay, this is part 1. Yeah? Everything that doesn't need to change is not going to change. Of course, we still have to model that something is changing. Yeah? And maybe the cursor is moving. This goes up completely. So what remains is part 2 and part 3. I'm going a bit over time, sorry for this, but good. And now somewhere on the way I lost my there. Good. And so 2. And next 2i minus 1 plus 2 times Pn plus 1. Same offset as in the other formula. Now what we need is a b. Yeah? So this means overwrite at position E, I, not I, A by B. Good. Next thing, we need to change the control state. So the last thing is free. And next, I think same offset, 2i minus 1 plus 2 times Pn plus 1. Plus 1 minus 2, sorry. We have P. Why the minus 2? Yeah, because delta QA was PB minus 1. This minus 1, we need to move 1 position to the left. We always have to multiply with a factor 2. So this is my minus 2. This minus 2 comes from this minus 1. P means that we are really in P. Yeah? So we really changed state to P. Good, this is the formula for one transition. Good, still it's in polynomial in the size of the Turing machine, etc. So we have a polynomial time reduction. And I hope it's not difficult to see now, if you understood the intuition, that the Turing machine accepts W if and only if there is a part in my transition system satisfying phi. Yeah, that's basically the way we constructed it. Good, end of proof. The last thing I want to say is that this is the complexity of the model checking problem. So the model checking problem is give me a transition system T, give me an LTL formula phi, and then the question is, does TS satisfy phi? Yeah, this is P space complete. What is interesting about LTL is that this is as equally hard as the satisfiability problem for LTL. You know the satisfiability problem for propositional logic is NP complete, right? Cook's theorem. The satisfiability problem of LTL is also p-space complete. This is p-space complete. What is the satisfiability problem? The satisfiability problem says, okay, give me an LTL formula phi. Yeah? Does there exist a TST such that T satisfies phi? Yeah? P-space complete. It's somewhere on the slides how to show this. This is also P-space complete. And by taking the negation, it also follows that the validity problem is a formula true for all transition systems is also p-space complete. Now, this is special about LTL. For many other logics, the model checking problem complexity-wise is much easier than satisfiability or validity. For LTL, they all fall in the same complexity class. Good, this was all about Turing machines, complexity. Next lecture, CTL, new logic. Hope to see you back on Friday.